Hello everyone, welcome to my new lecture series on problems in engineering thermodynamics. Myself T.Vignesh, working as an assistant professor in the Department of Mechanical and Mechatronics Engineering in SNS College of Engineering. In my previous video, we have talked about the problems in engineering thermodynamics. It's revolving around steady flow energy equation, where the systems are considered as a open system. There will be both energy as well as mass transfer will be there, and we have already seen 4 problems. If you haven't watched it, please go and see my previous videos. Okay, so this is the continuation of those 2 videos. So here the problem number 5 is talk about a balloon which is initially collapsed and flat, okay, is slowly filled with hydrogen gas at 100 kilopascal so as to form it into a sphere of radius 1 meter. Determine the work done by the gas in the balloon during the filling process. Okay, so this is a simple problem where initially the balloon is very flat. Okay, so you have to consider the sphere of radius at the initial process as 0 meter. So once you are going to fill the hydrogen gas, okay, at 100 kilopascal, the balloon's volume has been increased. Okay, so the sphere of radius comes around 1 meter. Okay, so for converting of this volume 0 to 1 meter, okay, the radius of 0 meter to 1 meter, the volume has been changed. Okay, so here you have to find out the work done in this process. So pressure is a 100 kilopascal. It is a constant pressure process because the whole scenario, the pressure has been kept constant, right? And then a radius of sphere at the end of the filling process is 1 meter. So initially it will be a 0. Okay, then you have to find the work done. Okay, so what will be the formula? You know that work done for this formula is P into del V. Okay, so work done W is equal to the W1 to 2 is equal to P into del V. Okay, so pressure we know, but the volume of a sphere, what is the formula? 4 by 3 pi r cube. Okay, here 4 by 3 and pi is a constant one. You have to substitute these values in the above equation, work done equation, where you can get W is equal to P into 4 by 3 pi r 2 cube minus 4 by 3 pi r 1 cube. Okay, here 4 by 3 pi is a constant one. You have to take it as a common one away from it, and you get the equation as W is equal to P into 4 by 3 into pi into r2 cube minus r1 cube. Okay, you know that radius of balloon initial and final, you have to substitute it, and you get a value as work done as 418.88 kilojoule. Okay, so this much of energy, this much of work done, okay, it's not, you have to give in order to fill the gas, that is 100 kilopascal, that hydrogen gas inside the balloon, to increase the volume or increase the radius from 0 meter to 1 meter. So this much of work done you have to give. Okay, you will see another problem, right? This is the problem number 6. In a diesel engine, okay, the atmospheric air at 300 Kelvin and 1 bar is compressed reversibly and adiabatically till the volume of air reduces to 1 by 16th of the original value. Okay, calculate the temperature and pressure of the air at the end of a compression and the amount of work done in compressing the air. Treat air as an ideal gas, gamma is equal to 1.4. Okay, so this is a basic question where pressure has been given. So it is a diesel engine where the air is compressed reversibly and adiabatically. Okay, so once the air is compressed, the volume reduces, and it reduces as 1 by 16th of the original value. Okay, so calculate the temperature and pressure after the compression. Definitely it will be increased during the compression, and also we are going to find out the work done for compressing the gas. Okay, So you know the value, that is P1 as 1 bar, T1 as 300 Kelvin, and the V2 by V1 as 1 by 16. Okay, and gamma as 1.4. Right. So what will be the formula? That is it is a adiabatic process. So T1 by T2 is equal to V2 by V1 whole to the power of gamma minus 1. This is the formula. Okay, so you have to substitute the temperature and volume ratio values, and gamma as we have to taken as 1.4, and with the help of this equation we have to find we will find temperature, that is temperature at the end of the compression as 909.4 Kelvin. Initially it was 300 Kelvin. After the compression the temperature will automatically increased, so it will becomes around 909.4 Kelvin. Okay, and for the pressure adiabatic process, that is P1 by P2 is equal to V2 by V1 whole to the power of gamma. Okay, so this is the equation. So you have to substitute the pressure and volume ratio values 1 by P2, then you will get the pressure at the end of the compression as 48.503 bar. Initially it was 1 bar. Due to the compression the pressure get increased and it increased up to 48.5 bar. Okay, so for work done formula, the W is equal to R into T1 minus T2 the whole divided by gamma minus 1, where R is a universal gas constant. It will be around 8.314, values 8.314, and the temperature we have already, the initial temperature has been given and the final temperature we find out, and substitute these values and you will get a work done as minus 12.66 kilojoule per mole. So this is a compression, so it is work done on the system, so it will be as a negative one. Okay, so because the work we have done as on the air, that is on the system. Okay, so this is the solution for this problem. Okay, so thank you so much for watching.